Okay. All right, so what we're going to do today is work through two illustrations, one of the ANOVA procedure, which is on assignment 12. And we also covered an example of this last week. So this is a refresher of how the ANOVA would work in R. And then we're also going to work through a regression example. As I mentioned before, so the regression example would be for part B of assignment 13. But from what I have been told, the lab exam will not contain regression. Okay, so this is truly extra material. So this illustration I will show you, I will work through it, I will describe what's going on, but it really is extra, like sort of some food for thought. And then once I'm done with those two examples, I'll just start to pick away at different illustrations. Maybe I'll go back to week one and work through some of the original examples that we had, just so you guys can get a refresher of the different concepts that we talked about, you know, from contingency table construction, scatter plots, or histograms, that kind of stuff. And then we'll just sort of work our way forward through the rest of the section. Okay, so we'll just do everything entirely in R Commander today. Let me just I'll do the regression quick. I just think that for completeness, we should do it because it's on there. And then I'll do it fast, I promise. You guys can take 5, but I think we should do it. Okay. Okay, so we're gonna start with exercise 33. And just for safety, we should do it, like just in case something changes at the last minute for whatever reason, which is very unlikely, but you know, just in case. All right, so where's my chat box? Okay, so let's do the ANOVA one. So we're doing demo question 33 from the, well, demo question 33. Okay, so students in 3 treatment groups, no fertilizer, liquid fertilizer, pellet fertilizer, monitored and recorded the number of days that it took until they could perform the first pruning for a basil plant they were growing in a class experiment. Then they calculated the average and standard deviation of days to the time of first pruning for their treatment groups, generally between about 35 days to 49 days. Data can be found in the file basil. We will perform an ANOVA test to determine if the mean growth significantly differs in at least one of the groups. Our significance level will be 5%. Okay, state your null and alternative hypotheses, and then it asks you to draw a background of the population to show what you mean. So we're not going to worry about this part. We're just going to work through what we actually have studied directly. So state your null and alternative. So the null hypothesis is equality across all means. So we have 3 different groups, which are the no fertilizer, liquid fertilizer, and the pellet fertilizer. So our null hypothesis here is going to be equality. Okay. And then the alternative is simply just going to be that a difference exists. So here what we would have is not all means are equal. Okay, state your assumptions. This isn't something that we've talked about directly, but just really quickly. So we would have SRS in each treatment population. Okay, we would have independent samples. We would have constant variance across each treatment population. And we would have normally distributed response variable. Okay, Use software to obtain an ANOVA table. Okay, so let's go through this again because this is probably the most important part of what we're doing. So we're going to start by opening up R. Okay, and then we're going to open up library RCMDR. Oh, there it is. All right, so we're working with that basal data set. So we are going to have here, I hate this. No. So data, import data from Excel. This will be question 33. And then we're gonna go here, 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 and then basal. So this is the basal data set. Okay, so when we take a look at this data, which is over here, all right? So we have in the first column, we have the group that it belongs to. So this first column is basically an indicator telling us the group. And then in the next two columns, we have different response variables. So in this question, we are measuring mean time to first pruning. So we want to know if there's a significant difference between time to first pruning among the different treatment means. Okay, so in RCMDR, we're going to go statistics, means, one-way ANOVA. One-way ANOVA is the only ANOVA that we've talked about. Our treatment, or the group, is going to be the treatment. That's the only categorical variable in the data set. And then we're going to have prune 1 as the response. Okay. All right, the significance level for the test is 5%, I believe. Yep. Okay, so we're gonna have, again, statistics, means, one-way ANOVA. Groups is the label that separates our response variable. So that's treatment for us. And then our response variable in this case is time to first pruning, which is prune 1. And then our confidence level will be 0.95 because we're using a 5% significance level. So we click OK. And then here is the output below. Okay. So if we copy this into the table, yep, they are the same. Okay. So we have the following output. So this is a summary of our ANOVA table for the experiment. All right, so state your test statistic. We can pull this directly out of the output. State the degrees of freedom. So we're going to have 2 degrees of freedom, 2 and 57. The p-value here is 0.00169. And the statement for this, or p-value statement and p-value, is going to be pf greater than 10.15 equals 0.00169. Use software to find the critical value for your level of significance, paste your output, and state the critical region. Okay, so in this question, what we are actually doing is we are using R commander to find an F value directly, and then we'll find the P value directly after that. Or just to find the F value directly because the P value is given. So in RCMDR, just like with any other distribution, if we want to find a critical value, we go distributions, continuous in this case, because we're working with the F distribution, and then F quantiles. So the quantiles are always the critical values. We type in the probability. There's no confidence interval associated with this. Also, just give me a second, Danny, because it's a completely, I understand it's related, but I don't have the assignment open right now. Okay, so this is going to be, okay, so the probabilities here, we're doing the 5% significance level, so we're going to type 0.05. We have 2 degrees of freedom in the numerator, and we have 57 degrees of freedom in the denominator, and it's upper tail. So we click OK, and that gives us 3.158843. So the critical region in this case will be reject H0 if F star, which is our test statistic, is greater than 3.158843. Okay, and then based off both approaches, we would reject. Based off the p-value approach, we would reject for the usual reasons. Okay, so since test statistic is in rejection region, reject H0 since p-value less than alpha. All right, state whether you have significant evidence to conclude that at least one of the population treatment means differ from each other. So we were able to reject H0, so we conclude that there is significant evidence that at least one of the population treatment means differs from the other, basically it. Okay, so yeah, that's pretty quick, ANOVA and R. Can you explain upper versus lower tail for this? Yeah, so with any F test, you're always in the upper tail. The rejection region is always in the, because it's a skewed curve, right? Right skewed curve. So we're always in the upper part of the curve. So here, when we do the significance level of 5%, that's telling us that the area is 5% in the upper, in the upper skewed part. So by clicking upper tail, we can put 0.05 in directly. If you wanted to put 0.95 in, then it would be a lower tail. But it's the same region, if that makes sense. Does that help? Yeah, that's the most direct way of doing it. Chi-square test and F tests are always upper tail, always. Because there's no direction. It's always in the upper tail. I just keep saying upper tail. It's always in the non-lower tail. All right, Danny, so let's take a look here. Assignment. Okay, so you are working on question 1. Yeah, so all this is saying to you is to confirm the ANOVA table in question 1. There's no confidence interval associated here. So let's just go over this real quick. Oh, let me share. Okay, so that's the end of that first ANOVA, the review ANOVA example. Again, with the ANOVAs, on the assignment anyways, it doesn't actually matter what you punch in for confidence level, because that doesn't apply to the table directly. So you can pretty much just put in anything you want there and you'll get out the right answer. For the regression part, we'll just really quickly look through this illustration. Some of the things about this will be review, which are nice from earlier in the course, earlier in the course. So we're going to use the dataset statistics student survey for R, and we want to create a scatter plot between before pulse min and before breath min. And before pulse min will be the response variable, and before breath min will be the independent variable. So in our CMDR, we go, we have to load the data first. So import from Excel, Q2, okay. So lab data. And then we have statistics survey for R. Okay, so if we want to build scatter plots in R, we go graphs, and then we go scatter plot. The X variable is BF breath min, and the Y variable is BF pulse min. Okay, so we click OK. And then here's our scatter plot, right? So actually that's review. That is review of something we learned very early on in the course. So actually going back to one of the questions that was asked earlier, like I don't remember September, that's a very fair comment. I don't remember last week, but one of the things that we did focus on were building plots. And almost every graph in R Commander, no, that's incorrect. Every graph in R Commander is found under the graphs tab. So that's actually kind of nice to know, right? Because if you need to build a histogram or a box plot or a scatter plot like we did here, they're all located in the same part of the R Commander screen, which is underneath graphs. All right, so here's our scatter plot for BF before pulse min versus before breath min. All right, so we'll just plug this in here. All right, and then that's all the question asked for. It just wants the scatter plot. So again, to do scatter plots, we would go graphs, scatter plot. And then you just need to place the correct variable on the correct axis. One of the nice things about this is if you do it backwards when you're building scatter plots, so say that you flip the variables by accident, you'll still get the right relationship. It'll just look, it's basically going to be like a mirror image of what you saw, but it'll still tell you the right trend. So you have a little bit of a safety net there. Okay, comment on the strength, direction, and form you see on the scatter plot. Okay, so this is a positive relationship. It's positive because as the X variable is increasing, the Y variable is also increasing. Okay, so positive relationships go in the upward sort of diagonal direction. Negative relationships go downward. So as X gets bigger, Y gets bigger, that's positive. As X gets bigger, Y gets smaller, that's negative. Comment on the strength and direction. The relationship appears to be fairly strong, though it does appear as the points deviate quite a bit around from a perfect straight line pattern. So it's definitely a positive relationship, but we see a lot of dispersion. So if you were to put a line down the middle of the scatter plot, you would see that the points are still quite a bit spread away from that line, as opposed to being like exactly on the line. Okay, find the line of best fit. So this is the most important part. If we want to do regression in R, we go statistics, fit models, linear regression. Right? Then we pick our response variable, which is pulse. We pick our explanatory variable, which is breath, and we click OK. And here's the output. Okay. All right, so the intercept is the first value here. Okay, so we have B0 is equal to 46.1865. And then the slope is the second value here. Okay, so this is 1.5101. Okay, so this is telling us when breath min is 0, the expected Beth pulse min would be 46.1865. And then this is telling us for every unit Beth breath min increases, for every unit Beth breath min increases, the expected Beth pulse min would increase by 1.5101 units. Okay, so these are standard interpretations of slope and intercept. And these are both things that we'll talk about in lecture, or you'll talk about in lecture as well. But basically the intercept is just telling us what y is when x is 0. And the slope is telling us, and the slope is telling us how much we would expect y to increase for a 1 unit increase in x. Strength is basically how tight are the points to the line. So if you imagine a straight line going through the data, how close are the points to that line? The more spread away they are, I would say kind of the less strong they are. And then the more the line kind of flattens out would indicate no positive relationship at all. Okay, find the correlation between Beth pulse min and Beth breath min. So correlation is equal to the square root of r squared. So what we would have here is that this thing is equal to the square root of 0.6851, which is equal to 0.8277. All right, and then R, and then using it from the correlation matrix outputs. All right, so if we go back to R, we would have statistics, summaries, correlation matrix, and then we would pick these two variables. Right, so actually here's another review, how to find correlation between two variables. So if we're looking for the correlation between two variables, we would go stats, summaries, and then correlation matrix. Then we would pick the two variables that we are working with. So we have Beth breath min and Beth pulse min. And then we would select the correlation we want, which is automatically done. This part is by default as well. We would click OK. And then you end up with the correlation on the off diagonal, so 0.8276697. And you can see that this is very close, actually identical to what we worked out above. So we have two ways of doing the same thing here. Sorry, I missed this part. So the line of best fit is just going to be y equals 1.5101. 46.1865, yes. Okay, perform a test to test the null hypothesis that there's no linear relationship between pre-survey breath rate and pre-survey pulse rate against the two-sided alternative. Determine if there is significant evidence that the slope is non-zero. Use the output. Okay, so just real quick here. This is the standard test within a regression setting. So the only hypothesis test that we're really interested in, at least at this level, is called the test of no linear relationship. The test of no linear relationship is done by testing whether or not there is evidence that beta 1, which is the slope, is equal to 0 against the alternative that it is not equal to 0. The rationale for this is that the line, the population line, is y equals beta 0 plus beta 1x. So if beta 1 is 0, then you have y equals beta 0, which would mean that X has no impact on Y. So by testing the null that beta 1 equals 0, you're actually determining if Y and X have a significant relationship with each other. Now, this test is done through a t-test. It's quite straightforward to do using our output. So you can see here that we have in the second column, or sorry, in the first column, we have estimate. In the second column, we have standard error. And then in the third column, we have our t-value. So we're going to take this value here. That's going to be the test statistic for the slope. That's our t-star. The degree of freedom below is given right here. So 58 degrees of freedom. Okay, the p-value is given in the last column. So right here. So what we would say in this part is p-value equals p t greater than 11.23 equals 3.51 to the negative 16. So that's basically 0. So we would reject H0 since p-value less than alpha. And then at the 5% significance level, there is evidence to support that the alternative is non-zero. Okay, so that's regression in a really quick summary, but at least you guys have the video after, so if you do want to review it for the assignment, you can. But again, I mean, the reality is that there's nothing that's going to actually test you on this, so probably something just for later on if you continue with statistics. Okay, so let's, spend the rest of the time doing a bit of review. I guess the natural place to start would be with you guys. So are there any questions that you have about any of the materials? The current assignment with the lab stuff, previous assignments with lab stuff, like anything in general? Otherwise, I'll just kind of try and pick apart at things that we haven't seen in a long time and whatnot. Sure. Yeah, that's a good question, Nicole. Let me see exactly what it says here in the outline. I mean, the thing is, like with next Tuesday's lab, the quiz already opened up, right? So you technically could finish it before. So according to the outline, we do not actually have a lab next Tuesday. So for that week, it's blank. So there's nothing in the outline about next Tuesday. So I guess, probably what I'll do is I'll just open the room, like the lab room, and I'll be here sort of as a consultant, more or less, if you guys have questions or anything like that. I think probably the rationale for that is just that it would be a little unfair for some students to have. Well, I guess if I'm sitting here, it's technically like a little bit unfair because all my YouTube links are on my channel. One sec, I'll give it to you. I just need to. Yeah. Yeah, like basically the videos are all labeled, so you just have to look for, I mean, if you want the lab session, I guess you can just search lab, or you can just look at the list of all videos, and they're all dated in order. So if you want last week's, you just have to find the lab that has last week's date on it, kind of idea. Need, okay, that's a histogram problem. Students completed a survey. This is, okay, this one looks like it's gonna work. Oh yeah, see, here's an example from something we did earlier. So let's just go over this, in this illustration to see the crosstab table, and then we can talk about those probabilities. So we have question 7 from the demo. Stat students at McEwen completed a survey. Raw data can be found in the file statistics student survey for R. You will create some crosstab tables from this data set and calculate some probabilities. For all probability questions, include a probability statement, a solution in fractions, proportion, and percent. Okay, so statistics student survey for R contains the columns Fed best, a variable that measures what federal party a student views as having the best party platform, and JT good, a variable that indicates whether a student feels Justin Trudeau is doing a good job as prime minister. Find the totals for each of the outcomes in the Fed best column. Find the totals for each of the outcomes in the JT good column. Make a crosstab table of the count for each of the JT good Fed best column. Use this information below. Okay, so first off, when we look at this data set, so this is always a good starting spot, right? So it's not this one. It's not this one. So we would do, no. Okay, so we're gonna go data. I swear I loaded this one. So this is gonna be Q7. Okay, so we have our statistics students for our data, view data sets. Okay, so when we look at this data set, yeah, I totally loaded this already. So we have Fed best, which is here in the 5th column. And these are all categorical outcomes, right? So categorical outcomes indicate right away that we're going to be focusing on counts. And then we also have the JT good column, which is still a categorical outcome because it's a yes or no, right? So our categorical or our qualitative variable, rather, those are labels. So we're dealing with qualitative data in this case. So in the course, when we think about qualitative data, the main thing that we should think about in terms of summarizing are contingency tables and bar graphs or pie charts. So for qualitative data visualization, we had the bar chart and we had the pie chart. Maybe just for illustration, let's go over those real quick. So let's say that we wanted to plot this qualitative data. So one of our options would be the bar graph. So we can do, where's Fed best? There it is. All right, and here's our bar chart for that. Okay, so you can see that for qualitative data, we're really focused on counts. So we have a count for each of the different parties. So 24 students prefer Liberal, 5 students prefer Green, 15 prefers Conservative, 16 prefer NDP. So when we talk about this, what we can basically discuss are what is the least preferred platform, what is the most preferred platform, that kind of idea. The only summary statistic that we can use here, since it's qualitative, is the mode. So in this illustration, the modal group would be the Liberal because it's the group with the highest count. So the mode is the only summary statistic that can be used for both quantitative data and qualitative data. And in the qualitative data case, it's simply the group with the highest count. So in this case, it would be the Liberal. All right, so we have the bar graph and the pie chart, or the bar chart and the pie graph, however it's said in R Commander. And they're both found through the same thing. So graphs, and then we have bar graph pie chart. And we only use those, again, when the data is qualitative, which is what we have here. Okay, if we want to summarize the information, we go summaries, and then we would go frequency distributions. And then we can click on fed best, click OK. And here's our frequency distribution for that variable. And the frequency distribution, as a reminder, is simply just a list that tells you the categories and then gives you the counts directly. All right, we can do the same thing for JT good. So statistics, summaries, frequency distributions, JT good. And then we have the following here. Okay, if we want to make a contingency table, we go statistics, contingency tables, two-way table, and then we select the variables. So we would have fed best and JT good. So one of the nice things about R Commander is really that, well, all of the different summarizing features that you would need, so the graphs and like these distributions, they're all kind of they're in a very logical place, right? So they're located underneath graphs and statistics. And then if you want a contingency table, I mean, that's just in contingency tables. Okay, so here's our output for the problem. And let's see what kind of questions we're getting asked here. All right, so what we've done here is we've taken our counts and we've just translated them into the full two-way table. So we have row totals here, column totals here, and then we have overall total here. As a reminder, this value 60 is found by adding only the values here and the values here together. This row total here is found by adding these values, this row total here by adding these values, and then these column totals here by adding each of the different columns. Okay, what is the probability that a student views the Liberal Party platform as the best platform and thinks that Justin Trudeau is doing a good job? So this is an intersection question, and it's asking us for the group that corresponds to both Liberal and Trudeau doing a good job. So for intersection questions, we would find directly the category that matches these two outcomes. So here we have JT good, and here we have Liberal. Okay, so this value right here. And then we would divide that by the total number of outcomes, which in this case is 60. In part C, it says, what is the probability that a student who views the Liberal Party as the best platform or thinks that Justin Trudeau is doing a good job? So this is a union question. For this question, we're going to use the general addition rule. So the general addition rule is P of A or B is equal to P of A plus P of B minus P of A and B. So in our case, we would have P of liberal or yes is equal to P liberal plus P yes minus P liberal and yes. So P of liberal is going to be 24 over 60. That's a marginal probability. P of yes is going to be 35 over 60, another marginal. And then the intersection is what we found in the previous question. So that's 23 over 60. If we work this part out, we have 36 over 60, which is 60%. All right, in part D, we have, what is the probability that a student who views the Liberal Party as the best platform thinks Trudeau is doing a good job? So this is a trickier question because the language makes it harder to understand what direction the condition is working in. So when we read part D, first off, we have what is a probability? Whatever. And then it says that a student who views the Liberal Party as the best platform. Okay, so what this is telling you is that this student already views the Liberal as the best. So right off the bat, it's saying to you, the student has this condition. The student thinks the Liberal Party platform is best. Therefore, that statement forms the condition. Okay, so we know already the student thinks liberals are best. So we check that off. Then it asks to us, thinks Trudeau is doing a good job. So what this is saying is, given they think the Liberal Party is the best platform, what is the probability they think Trudeau is doing a good job? So this is the probability of yes given Liberal, which is the probability of yes and Liberal over the probability of Liberal. And those values we have already worked out. So you can see here, we just end up with 23 over 24, which is 95.8%. In part E, we're going the other way now. So now it's telling you, given the student thinks Trudeau is doing a good job, what is the probability they view the Liberal platform as the best platform? So now we have Liberal given yes, which is Liberal and yes over the probability of yes. So the only thing that changes here is the denominator. So now we have 23 over 35 once we simplify, which is 65.7%. Any questions? We still have 25 minutes left. Will it be explained easier on the final, like on the midterm? This isn't gonna, like on the lab exam final? Well, on the lecture final, this isn't gonna be there. On the lab exam final, it'll be the same language that was used on the quizzes. The lab quizzes. Okay, so there's a few more. Do you guys want to do some more probability ones? Do you want to look at something else? Let me just pick something. Okay. Do you have a preference or just anything else? Surprise us. Yeah. Pick with a K. Thank you. All right. Oh, here, let's do the binomial stuff. I mean, the next thing. It's probably been a while since we've seen that, right? Is this the only? Okay, yeah, let's do this. Okay, let's try number 9. So consider a binomial experiment where 100 independently random chosen university students are asked a yes or no question, where the probability of success is equal to the probability a person answered yes. Use software to answer the following questions fully. Okay. So yes or no question. So first off, as a reminder, a binomial experiment is an experiment that consists of n Bernoulli trials. A Bernoulli trial is a trial or an experiment in itself, and it is a very specific experiment. It is one where whatever you do, you only do it one time, and the outcome is one thing or its complement. So the Bernoulli experiment refers to, for example, a coin flip. If you flip a coin one time, you get a head or a tail, and those are considered complements of each other. So opposites, if you will. In this question, basically what we are told is that for every situation, we have 100 independent students. So we have 100 as little n, which is our experiment repetition size, or the number of repeated trials, or the sample size. So in part A, the yes or no question is, can you program in C? So P equals 15% said yes. So we have a probability of success of 0.15, and we have little n is equal to 100 for every single experiment. Find the probability that between 12 and 18 students can program in C. Okay, so where this is going to get confusing right off the start is not being able to recognize the type of problem. Because if you read this statement and you haven't already been able to identify this as being a binomial experiment, right away you're going to be very intimidated by this kind of probability question. So again, the thing that makes this binomial is you have consistent sample size, so 100. Every single student is independent, and every student is asked the same yes or no question. So every student can only contribute yes or no, which is a Bernoulli outcome, this thing or the opposite. So in this question, we want to find the probability that between 12 and 18 students inclusive can program in C. So there's a number of different ways that we can do this in RCMDR. When we use RCMDR for binomial calculations, we go distributions, discrete, binomial, and then we go binomial probabilities or binomial tail probabilities. Now, if we click binomial probabilities in this particular question, the output is going to be massive. So we're going to have, as the number of trials, 100, and as probability of success, 0.15, because we're considering yes, the answer yes to be a success, and there's a 15% chance that happens. So we click OK. You can see like R wants to blow up right now. Maybe it will. If anything, this is the best way to end the lab portion of the course, with breaking our commander. What if my computer breaks? No, it's still alive. Yeah, I'm sure that'll fly. Okay. So as you can see, that first option using binomial probabilities is not the best option. Okay, so in that case, what we're going to do is we're going to use the tail probabilities command. And that's just because the sample size is so large. If n was not 100, if it was something like 10 or 15, it would be fine. So RCMDR. Okay, so we're going to go distributions, discrete, binomial, binomial tails. So what the binomial tail probability gives us is the probability of being less than or equal to that number. So we can type in 12 and 18 here. We can tell it there's 100 outcomes, and we can tell it the probability of success, and then we want the lower tail. So we basically, what we're going to do is we're going to find the probability of being less than or equal to 11, actually. So strictly less than 12, less than or equal to 18. And then we're going to subtract off the part that is strictly less than 12 or less than or equal to 18. So we have 100 trials, probability of success 0.15. And these are the two variable values. So we need everything less than or equal to 11 because we want 12 to be included in the calculation. And we want everything less than or equal to 18. So we click OK. And then you can see that RCMDR spits out these two numbers here. So if we go back to our Microsoft Word page, we have the following. All right. And then all we have left to do is write out the statement. So we want X between 12 and 18 inclusive. So that's X less than or equal to 18 minus X less than or equal to 11. This is the same thing as X strictly less than 12. And then we just pull the two numbers out from our output, and then we end up with the probability that we need here. All right. So in part B, it's the same style of question. So the question is now, do you have a vegetable garden? The probability that you say yes to this is 28%. And you want to find the probability that more than 26, but less than 31 have a vegetable garden. So more than 26, less than 31. So this is P27 less than equal to X less than equal to 30, because we're not including 26 and 31 in the calculation. So now what we're going to do is find Px less than equal to 30. And then we're going to subtract off Px is less than 27, which is Px less than equal to 30 minus Px less than equal to 26. All right. So then in RCMDR, we would have the same idea as before. So we're going to go distributions, discrete, binomial, binomial tail. So we're going to have 26 and 30, was it? Yep. So 26 and 30, 100 trials, and the probability of success was 0.28, I believe. Yes. Then we click OK. All right, and we end up with the following. And then you can see here that we're going to have this minus, okay, and then that gives us and then, sorry, and then that gives us, 0.3401, so roughly 34.01%. All right. Okay. Another binomial one, or do you guys want to see something else? Okay. Okay, well, let's check out this one. So this is a normal question now. So assume that the wingspan of a certain type of monarch butterfly is normally distributed with a mean of 10.3 and a standard deviation 0.6. So in part A, it says find the probability that a monarch butterfly has a wingspan of no less than 11.2. No less than 11.2. So that would be greater than 11.2. So what we have here is probability X greater than 11.2. It's a normally distributed random variable. So now what we have to do is convert this to a Z-score. So we're going to have Z is less than X minus mu divided by sigma. Sorry, Z is greater than X minus mu divided by sigma. Okay, so this is the probability Z greater than 11.2 minus 10.3 divided by 0.6. All right, and then that's going to be the probability Z is greater than, and I don't actually think we need to take this any further, but just for completion's sake, so we would have 11.2 minus 10.3 divided by 0.6, I believe it was. Okay, 1.5. Okay, so now what we can do is two things. In our CMDR, we can go distributions, continuous, normal probabilities. Okay, so if we want to use the standard normal, we've already converted to a z-score. So here we would just type in 1.5, and then we would click upper tail because we want the probability of being greater than 1.5. So that gives us 0.0668072. The other option is you don't even have to convert it. You can just go distributions, continuous, normal probabilities. You can type in your values, so 11.3, 10.5, 0.6. So this will give us the probability that X is greater than 11.3 with a mean 10.5, standard deviation 0.6. We click OK. Whoa. Oh, sorry. My bad. There we go. Why are those so different? Okay, and then you can see that you get the same number out. In part B, find the probability the monarch butterfly has at most a wingspan of 8 centimeters. So we would have X less than 8. Okay, and then if we wanted to, again, we can skip a bunch of steps here and we can go distributions, continuous, normal probabilities. In this case, we have a lower tail, plug in 8, and then we get out our answer. And then if we wanted to, we could confirm this by converting to a z-score. So this is going to be the probability z is less than 8 minus 10.3 divided by 0.6, which is negative 3.833. Okay, and then if we were to take that approach, we would go distributions, continuous, normal probabilities. We would have negative 3.833333, 0, 1. And then you can see you get the same number. We're very close to the same number out. There's just a little rounding there because of the repeating 3. Okay, here's another good one. So here we have a monarch butterfly with a wingspan in the bottom 2% of wingspans is considered exquisite. Find the highest wingspan that a monarch butterfly considered exquisite will have. So what we want to know here is what value of X marks the second percentile. Okay, so that's what this is asking. It's saying the bottom 2%, so from 0 to 2%, are an exquisite butterfly, so a very small butterfly. So what value of X marks the second percentile? So we need to know first what value of Z, so what value Z naught is equal to 0.02. Okay, then we convert X equals Z times sigma plus mu. Now in our CMDR, we can actually get around this very easily. So what we can do here is distributions, continuous, normal, and now we want a quantile. It's a lower tail quantile, so we type in 0.02, 10.3 for the mean, 0.6 for the standard deviation, and that gives us 9.067751. So now if we wanted to do it the other way, so using the conversion technique, what we would do then is we would find the z-score that corresponds to the second percentile. And this would be basically how you do it by hand. So we would go 0.02, 0.1, click OK. That gives us negative 2.053. And then we would multiply that by sigma and add the mean. And then you get the same number out. And then in the last question, it says, what is, oh, I see. So all this work is below, so it's just being repeated, but okay, a monarch butterfly with a wingspan in the top 1% is considered extraordinary. So this is actually the exact same question, It's just a different percentile. So if we're in the top 1%, we're actually talking about the 99th percentile. So PZ less than Z0 equals 0.99. Okay, so this is the exact same problem. So we can do this in a couple of ways in R Commander. We can go distributions, continuous, normal, normal quantiles. If we type in 99% directly and we just give it the mean and the standard deviation, then we're done. If we wanted to, we could also write it down exactly as it appears. So if we put 1% in, we just have to make sure we flip to the upper tail in that case. Okay, and then we end up with 11.69581. So the wingspan to be considered extraordinary is extraordinary. Okay, so the sampling distribution stuff, that's in the next unit. This is actually very similar. The only difference is here is that the z-score is going to be divided by, or the sigma for the z-score is going to be sigma over the square root of n, right? So I think I'll stop here because there's only 3 minutes left. I'll hang around if you guys have any questions, but otherwise, I hope that the labs were helpful. I think that in some aspects the lab works pretty well online, to be honest, because of the nature of it. And if you guys have any questions about the quizzes or whatnot, let me know. And you know, if any other information comes out, I'll share it with you as soon as I can. But I think that you'll get an email from the lab coordinator regarding the structure of the test and all that sort of thing. And otherwise, yeah, I'll be available next Tuesday at this time. I'll kind of treat it as an office hour. And then if anyone wants to drop in with questions, if you want to rate your quiz during that time, I'll hang around. So, or I'll be around. Otherwise, good luck with everything. And yeah, well, I guess good luck with everything and the rest of your some classes and next semester and all that sort of stuff. And then hopefully we'll all see each other on campus next fall. Take care.